Hello. Today I will go over limits, the backbone of calculus, how they work and why. I hope you enjoy the video. So we have to start with functions. We should all be well aware of how they work. We define f of x as this, and then evaluate it at, let's say, 2. Just sub everything in, and we get that it's equal to 8. This works well on most functions and most of their points. But now, what happens if I give you this function and tell you to evaluate it at 4? Alright, nice and simple. Just put in 4 for x. Now let's look. The numerator becomes 0, and now for the denominator. Oh no, that became 0 as well. Oh god, we have 0 divided by 0. This is called indeterminate form because we can't determine its value. So something must have gone wrong here. Let's try another method. I've got our function graphed right here, and if we go to our problem point, we see, just as we thought, it's undefined. But what if, instead of trying to evaluate it at its undefined point, we look really close to it? Because, it's right there, as you can see. So we can just zoom in, we can look, oh look, over here it's defined, but when we go over to it, it's undefined. So what if we look at the numbers close to it? Instead of evaluating it at 4, we can evaluate it at, let's say, 3.9 and 3.99. We get 11.9 and 11.99999. Then we can try from the other side, 4.1, we get 12.1. 4.001, we get 12.00001. Almost seems like we're approaching a value, and that value seems to be 12. So maybe if we evaluate it at 4, it's almost like it should be 12. Now, this is called taking a limit, where we examine the undefined part of a graph using the information that we can gather by observing the areas next to it, just like we did here. Now, it's nice to say that our function equals 12 at 4, but we can't be 100% sure. What if it was 12.000000001 and we just didn't check close enough values? So we can try to attack it from a different angle. What if we rewrite our function so that it behaves the exact same way everywhere, but it's defined at 4? We can construct it starting from f by simplifying it. So what's happening is it's a fraction, which is causing the 0 divided by 0. So what if we can get rid of the part of the fraction causing it? We will get rid of the 0 divided by 0. So let's look at the numerator. It's a quadratic. What if we factorize it? We get back x minus 4 times x plus 8. If we look at this, it's divided nicely by x minus 4. In fact, the x minus 4's cancel out, leaving us with just x plus 8 as our new function, which should behave identically as we only simplified. So now let's quickly evaluate it at x equals 4. And yes, we get 12. So our limit of f at 4 is 12, just as we thought. Now our limit is written like this. The lim is denoting that we are taking a limit, and the x with an arrow pointing to 4 is just what number we are approaching in our limit. So now let's look at 1 over x. Something really odd happens here when we evaluate it at 0. We get 1 over 0. Now that's just infinity, right? No, absolutely not. We'll have to take a limit. If we look at it from the right, let's say by trying 0.1 and 0.001, continuously getting smaller, it looks like at 0 it should be approaching infinity. But that's just the right-handed limit, denoted by the small plus over the 0. If we look at it from the other side and test minus 0.1 and minus 0.01, we see it's approaching negative infinity. This is the left-handed limit, denoted with the minus. These two limits being different means that the limit doesn't exist at 0, and that we have to specify which side we are approaching from. This is usually more important for piecewise functions, especially on their boundaries. Now, one more thing we can do with limits is take the limit as x approaches infinity, since there's nothing stopping us. Now, how this works is, let's say f is this. We can try plug in infinity and we just get infinity over infinity, but this is another indeterminate form, just like 0 divided by 0, as it doesn't give a clear answer. But we can notice something. Not all terms in this are important. Let's say we look at the numerator and how each term grows. One clearly grows the fastest, 3x cubed, which means as this term approaches infinity, it becomes the only important term. If we do the same for the denominator, we find the fastest growing term is 2x cubed, so we can just evaluate this limit. Now, if we simplify this, the x cubed terms cancel out and we are left with 3 over 2, which is our limit. If we check the graph, yes, it follows this limit. Now I'll leave you with some practice problems, if you'd like to try them out. The answers will appear in 10 seconds. Here are the answers to the previous questions. So thank you for watching. I hope you learned something new. If you have any video suggestions, please leave them down in the comments. Thank you and have a nice day.